Imagine a simple login form. It looks harmless, just a username and password box. But if the system is not built securely, that small input field can become a doorway for attackers. This is how SQL injection can cause serious damage to websites, databases, organizations, and normal users. First of all, what is SQL injection? SQL injection, also known as SQLI, is a web application vulnerability where an attacker inserts malicious SQL code into an input field. SQLI can allow attackers to gain unauthorized access, view confidential information, modify records, delete database contents, gain admin privileges. SQL injection is dangerous because attackers may use it to extract large amounts of sensitive data from database. SQL injection happens when user input is accepted by a web application. The web application processes it and creates an SQL query to send it to the database. However, an attack may enter malicious input such as or1 equals 1. The query may become select all from users, where username equals 2 or 1 equals 1. The condition 1 equals 1 is always true, so the attacker changes the meaning of the query. This can cause the database to return data that should not be accessible. The main types of SQL injection include in-band SQL injection, blind SQL injection, error-based SQL injection, and out-of-band SQL injection. In-band SQL injection happens when the attacker uses the same communication channel to inject SQL code and retrieve the result. The stolen data may appear directly on the web page. Blind SQL injection happens when the application does not show database results directly. The attacker observes how the website behaves by sending true or false conditions repeatedly. The attacker can slowly infer information from the database. Error-based SQL injection happens when attackers intentionally cause database errors to reveal information about the database. Detailed error message may expose the database version, current database user, table names, column names, and database structure. This type of attack is often used to gather information before launching more advanced attacks. Out-of-band SQL injection retrieves data through a different communication channel such as email or another external connection. This technique may be used when normal data retrieval is limited, but outbound database connections are weak. The common causes of SQL injection are mostly related to insecure coding and weak database security practices. These include poor input validation and sanitization, improper use of dynamic SQL, weak encoding, unsecured legacy code, excessive database privileges, poor error handling, and inadequate security testing. To prevent SQL injection, effective countermeasures must be applied. If a vulnerable query is used, an attacker can insert malicious SQL commands into user input fields. The database may interpret the input as part of the SQL command, causing unauthorized access, such as bypassing the login system. Therefore, the first and most important countermeasure is using parameterized queries, also known as prepared statements. Prepared statements prevent SQL injection by separating SQL code from user input. The database can identify which part is the SQL statement and which part is only user data. For example, instead of directly inserting a username into the SQL query, a prepared statement uses a placeholder, select all from users where username equals. This tells the database, I need to search for a username. The next input entered is only a value, not part of the SQL command. So, if an attacker enters a malicious input such as OR1 equals 1, the database will treat it as a normal username value instead of executing it as SQL code. Since the value does not match any username in the database, the login attempt will fail. The next countermeasure is input validation. Input validation checks user input before the system processes it. It ensures that users enter valid data in the expected format and prevents harmful input from reaching the database. There are two common types of input validation: whitelist validation and blacklist validation. First is whitelist validation. For example, username rules can be: only allow letters from A to Z and numbers from 0 to 9. No spaces or special characters are allowed. If a user enters John 123, the input is accepted. However, if the user enters OR1 equals 1, the input is rejected because it does not follow the validation rules. Next is blacklist validation. Blacklist validation blocks known malicious patterns or keywords, such as OR1 equals 1, and union select. However, blacklist validation is weaker because it only blocks specific patterns. Attackers can modify their input to bypass the filter. For example, if the blacklist only blocks OR1 equals 1, an attacker may enter OR equals A, which may bypass the blacklist. This can trigger an alert. Input may bypass blacklist filtering. Possible SQL injection attempt detected. Therefore, whitelist validation is the recommended approach because it only allows predefined and valid input while rejecting anything that does not follow the rules. Next is database auditing and monitoring. Database auditing works like a security camera for the database by recording and reviewing database activities. It can monitor events such as login attempts, access to sensitive data, data modifications, administrative changes, and suspicious activities like repeated SQL injection attempts. This helps organizations detect attacks earlier, investigate security incidents, and identify who performed specific actions in the database. Another layer of protection is a web application firewall, also known as WAF. A WAF acts as a security barrier between users and web applications. It monitors, filters, and blocks suspicious HTTP or HTTPS requests before they reach the web server. A WAF can detect SQL injection using methods such as signature-based detection, anomaly-based detection, and behavioral detection. However, a WAF cannot fix vulnerabilities in the application code. It should only be used as an additional protection layer together with secure development practices. Another important security principle is the principle of least privilege. This means users, applications, and processes should only receive the minimum permissions needed to perform their tasks. For example, a customer portal may only need permission to view records, while an administrator has higher privileges. This reduces the damage if an attack happens because attackers cannot access unnecessary data. A real-world example of SQL injection impact is the TalkTalk data breach in 2015. Attackers exploited an SQL injection vulnerability and gained unauthorized access to customer information. This incident shows that SQL injection is not only a theoretical problem, but a real threat that can cause financial loss, reputation damage, and exposure of sensitive data. Although the main focus is SQL injection, another related security issue is buffer overflow. A buffer overflow occurs when a program writes more data into a memory buffer than it can handle, which may overwrite nearby memory and cause system crashes or allow malicious code execution. To prevent buffer overflow attacks, developers should use safe coding practices such as bounds checking, safer input functions, secure libraries, and memory protection techniques like ASLR and DEP. In conclusion, SQL injection is a serious security threat that can lead to data theft, system damage, and unauthorized access if not properly prevented. We learned how SQL injection happens, its different types, and the common weaknesses that cause it, such as poor input handling and insecure coding. To prevent these attacks, multiple security measures must be used together, including prepared statements, input validation, database auditing, web application firewalls, and the principle of least privilege. Real-world cases like the TalkTalk data breach show that SQL injection is not just theoretical, but a real and dangerous threat. Lastly, let's protect our systems with defense in depth and prevent SQL injection to keep our data secure.